So, what does a drug like methamphetamine actually do to the human brain? We're not just guessing here. We're going to take a look at the hard evidence from neuroimaging research. The scans that let us peer deep inside and see exactly how this substance can change the brain's physical structure and even its basic chemistry. Let's just kick things off with a question that honestly sounds like something out of science fiction, but it's at the very heart of the latest research. Can a drug literally make your brain age faster? And the answer, based on a whole lot of studies, is a pretty startling yes. Neuroimaging is showing us that for many methamphetamine users, their brain age, the actual physical condition of their brain, is years, sometimes even decades older than their real chronological age. So you have to wonder, how is that even possible? Well, it all starts with the brain's physical structure. Let's dive in and see what MRI scans reveal about the large-scale, visible damage. Okay, this table really lays out the stark physical evidence. When you compare MRI scans from meth users to a healthy control group, the differences are just dramatic. Take a look at that BV/CSF index. It's lower in users, and that's a direct indicator of brain atrophy. We're talking about the brain literally shrinking. And then you see a larger volume of white matter lesions and a larger choroid plexus. Both of those are clear signs of widespread damage. So what in the world are these white matter hyperintensities? Well, think of your brain's white matter as its information superhighway, all the connections that let different parts talk to each other. These hyperintensities are like potholes or lesions scattered all over that highway. They're areas of damage that just mess up and slow down communication across the entire brain. And this kind of structural damage, it has devastating real-world consequences. It's a direct risk factor for the early onset of serious neurological conditions that we usually associate with old age. I mean, things like stroke and even dementia. So we've seen the big picture structural damage, but to really get what's going on, we need to zoom in, way in. From those physical highways down to the microscopic chemistry that actually powers them. And specifically, we're going to look at the brain's reward system. The number one target here is the dopamine system. That's the brain's master circuit for pleasure, motivation, all the things that make you feel good and want to do things. But here's the thing, methamphetamine doesn't just activate this system, it completely hijacks it. And you don't have to be a neurologist to see the difference here. These are PET scans. See the bright, fiery orange and red areas in the bottom image? That's the non-user, and it shows high levels of dopamine transporter activity. Now, look at the top image, the user's brain. It's so much dimmer, cooler. That's a huge, visible reduction in a really critical piece of the brain's chemical machinery. So what are these dopamine transporters, or DATs? The easiest way to think about them is as the brain's dopamine cleanup crew. See, after dopamine delivers a pleasure signal, the DATs swoop in to remove the excess and get the system ready for the next signal. The problem is, methamphetamine directly damages this cleanup crew. And the damage is pretty serious and really consistent. Across a bunch of different studies, scientists have found that chronic users have somewhere between 15 and 28% fewer of these critical dopamine transporters in a key reward area of the brain. So that cleanup crew we talked about, it's severely understaffed. Okay, so we've got structural damage and we've got chemical disruption, but what does that actually mean for a person day to day? Let's connect these brain changes to how someone actually functions in the real world. How does all this damage affect their ability to just think? Well, the fallout is widespread. The damage we've just seen translates directly into problems with the most fundamental mental abilities. We're talking about trouble with attention and concentration, problems with learning and memory, and a really big hit to what's called executive function. You know, the very skills like planning and decision-making that we all rely on to just navigate our lives. And here we can see what's happening during those decisions. In a healthy brain, the prefrontal cortex, think of it as the brain's CEO, it lights up, it's active, it's weighing consequences. But in a user's brain, that same exact area shows much less activity. The CEO is basically asleep at the wheel, and that leads to much more impulsive, reactive decisions. So all of this paints a pretty grim picture, I know. And that leads us to what is probably the most important question of all. Is any of this damage reversible? Can the brain actually heal from this? And the research here gives us a little bit of hope, but also a really stark warning. On one hand, some of the brain's chemistry can bounce back. Studies show that the levels of those dopamine transporters can actually get back to normal after about a year of abstinence.
But, and this is a huge but, the cognitive problems, the issues with memory, attention, and motor skills, they often stick around.
This timeline makes that gap incredibly clear. In early abstinence, those DAT levels are still really low. Then, after about a year, maybe a year and a half, they might start to look normal on a brain scan. But even further down the road, the functional problems, the trouble with thinking and memory, can still be there. This is so important. Chemical recovery doesn't automatically mean functional recovery. So that brings us to a really fascinating puzzle. If key parts of the brain's chemical system can be restored, why do the cognitive problems hang around for so long? Well, the leading theories point to a few key reasons. First, the brain isn't like a car engine. You can't just replace one broken part and expect everything to run perfectly. It's a deeply interconnected network. Second, some of that structural damage we saw earlier, remember those potholes on the information superhighways? That might just be permanent. And finally, it could be that other critical brain systems that help us think just take much, much longer to heal, if they ever fully do. And that leaves us right on the cutting edge of addiction science. The ultimate goal for researchers now is to go beyond just describing the damage. The dream is to be able to use these very same brain scans to predict an individual's path to recovery, and maybe even design personalized treatments to help heal the brain. A future where we can not only see the problem, but also see the path back.